So let's go through a full graphical and analytic derivation of a Fourier transform. So we're interested in the Fourier transform of this function here, e to the at times u of t, whenever a is less than 0. So we're going to split this into its even and odd components, and we'll find the Fourier transform of the even component and the Fourier transform of the odd components, and when we add them together we'll get the final Fourier transform. And then we'll just find the Fourier transform of this and make a comparison to see they are in fact the same. So we can work out the even and odd components of this function as we've seen before. The even component is given by f of t plus f of minus t upon 2. So that gives us on the left hand side a half e to the minus at times u of minus t, and on the right side hand side is a half e to the at times u of t. And the odd components are going to give us a half e to the at u of t and minus a half e to the minus at u of minus t. So you can add these up and see that you get back to this function here. So let's go and we'll have a look at the even components here, and we'll have a look at the Fourier transform of this function. So here's the function here, the even components. And this is the Fourier transform here, and you can see that the Fourier transform is a purely real function of the frequency. There's no imaginary part here, and this is the shape of it here. Now we're not interested in what the actual analytic value for this is at the moment. All we're interested in is just to have a little graphical look at the shape of it. So we'll go ahead and look at it in MATLAB and show you how to produce this yourself. So let's generate the Fourier transform of that even component. So again, you can use this f1, which is the function that gives you your Fourier transform. So you can type in f1, and this is the function here. Okay, so you can take a note of that function if you want. I'll also put a wee note of it in the resources section. And we're doing the Fourier transform from, let's say, minus 10 to 10. So this is the Fourier transform here. Now it might look a bit messy at the moment, but you note that the scale on this imaginary axis is minuscule. Okay, so if we turn it around here, you can see that we've got a purely real function of the frequency, and this is the shape of it here. Okay, so you can go ahead and you can generate that for yourself. Okay, and this is the odd part here. So we have our minus a half e to the minus at u of minus t. We have a half e to the at u of t. So this is the time function here, and it's the odd part over e to the at. So the Fourier transform of that is this function here. And you can see that this function is a purely imaginary function. There's no real part to it. So let's go ahead and we'll produce that in MATLAB. So again, we're going to use this function f1 to generate the Fourier transform. So we can type in our f1. Now this is our function here. Again, I'll make that available to you in the resources section if you're unsure of it, or you can just copy it from the screen. And we'll do it from, say, minus 10 to 10. And again, there's our time domain signal at the bottom and our Fourier transform at the top. Now again, the Fourier transform looks a bit messy, but notice one of the scales is absolutely minuscule. The real scale is 10 to the minus 16, so it's non-existent. So if I was to turn this round to the purely imaginary axis, and there we see we've got the Fourier transform of this function here, which is a purely imaginary function. So now what we can do is we can go and find the Fourier transform of the actual function e to the at, and we'll split it into our real and imaginary parts, and you'll see that both of them match up. So now we've added the even component to the odd component in the time domain and got back to our original function e to the at times u of t. Now we've seen from the last two slides that the even component of this gave us the real component of the Fourier transform, and the odd component of this gave us the imaginary part of the Fourier transform. So if we've done this right, when we added both of these up, we'll have the Fourier transform here, and it should have the real even part and the imaginary odd part worked into this strange little shape here. Okay, so this is a Fourier transform of this function, and I've showed it in the 3 dimensions with imaginary and the real. So we'll get it to MATLAB now, and we'll move this round about in 3 dimensions, and we'll get back to just the real part and the imaginary part. So again, we'll use this little function f1, so we can type in f1, and the function we're interested in is this here, is e to the minus x times heaviside x. Now you can just take a note of that yourself, or I'll put a note of it in the resources section, and we'll go from say minus 10 to plus 10. And there we go, that's that function that we just seen a minute ago. So now, if I was to move this round about to rotate it, I should be able to see the real part and the imaginary part, and they should be the same as what we got for the purely even and the purely odd function. So let's get to the real part. So the real part is that there. Okay, so that's exactly what we've seen whenever we looked at the Fourier transform of the real part of this function. Now, the Fourier transform of the even part of this function. So let's move it round to the imaginary side. So here's the imaginary there, and there you go, that's the Fourier transform, and we're looking at only the imaginary part. So that there is the Fourier transform, and it's the same shape as the odd part of this function. Okay, so there you can see then, it shows you clear as day that if we were to find the Fourier transform of the even part of the function, we're going to get the purely real term, and if we look at the Fourier transform of the odd part, we're going to get the purely imaginary part on the frequency domain. So let's go and look at these analytically. So let's look at what we've done analytically and start putting some equations to some of the graphs that we've been looking at. So we've been interested in finding the Fourier transform of a function e to the at u of t. So the form the integral from minus infinity to infinity of our function times e to the minus I omega t by dt. Now we notice that the u of t is only defined as a value of 1 for t greater than 0, so greater than or equal to 0. So that means that we can form the integral there from 0 to infinity of e, and we can take out our common factor over t. We're left with our a minus I omega. Now when we integrate this, again the exponent just comes down, so you end up with 1 upon a minus I omega e to the minus I omega t from 0 to infinity. So when we put infinity in for t, that's going to be e to the minus infinity, so that's going to be e to the minus x as x tends to t tends towards minus infinity, so that's going to tend towards 0. And then if we put a value for 0 in for t, then that's going to be e to the 0, n to the power of 0 is just 1, so this is going to be minus 1 upon I omega minus a. So it means that the Fourier transform pair for e to the at u of t is 1 upon I omega minus a. So this function here, 1 upon I omega minus a, that's the function which we've seen in the previous page there, which was the strange shaped function which we looked at in terms of the real and the imaginary parts. So we'll see it again in a minute anyway. So what we're interested in doing now is we want to split that function down into the real even parts and the imaginary odd parts. So we'll go and do that in the next slide. So we're looking at taking the function at I omega and splitting it into the real even part and the imaginary odd part. So what we can do is we can take our function there, which is a 1 upon I omega minus a, so that's a complex function, and if we multiply it top and bottom by a complex conjugate, so the I omega becomes minus I omega, so we're multiplying it with this here, then we've got this line here, minus I omega minus a all upon omega squared plus a squared. Now I suggest you work through these and convince yourself that you get this bottom line here. So then we can split this simply into the purely real part, which is going to be the minus a upon omega squared minus a squared, and the purely imaginary part, which is minus I omega upon omega squared plus a squared. So that means that this function that we were looking at before, which is the purely even function of time, which is given by this. Okay, so that's the even function of our e to the at u of t. So that's Fourier transform of that is going to be given by our minus a upon omega squared plus a squared. And the purely odd part of the function of time is given by this function, and that is the imaginary odd part, and the Fourier transform is given by minus I omega upon omega squared plus a squared. Now we'll look at these just in a minute in the actual graphical form, okay, and you'll see where it make it a bit easier to understand. Now we don't usually write it like this, but we usually have seen it written in terms of a magnitude and a phase of a complex exponential. So in this case the magnitude is given by 1 upon root of omega squared plus a squared, and the phase is given by inverse tan omega upon a. So let's have a wee look at this in a bit more detail, and we'll see where this comes from, and we'll put these against the actual graphs, the equations against the graphs, okay? Okay, so we have actually 6 figures here. So this figure here is the function of time that we want to find the Fourier transform of, so that's our e to the at u of t. The top function here is the actual Fourier transform, which is our 1 upon I omega minus a, which we just worked out analytically in the last slide. I've also split it down into the real even part of this function and the imaginary odd part of the function. So the real even part is given by minus a upon omega squared plus a squared. So we're saying that this actual function here, this is the analytic version of this function, and the imaginary part is given by our minus I omega upon omega squared plus a squared. So this is the analytic description of this imaginary odd part of this function here. But as we said, that we don't usually see them drawn out like this. We'll see them drawn out in terms of a magnitude and a phase. Now, just to be clear here, it's something that's maybe not described or explained in much detail, but in this instance here, we had this Fourier transform of this function, which is a complex valued function, but we want to split this complex valued function into a magnitude and a phase. Now the magnitude and the phase are dependent on the frequency. So the magnitude and phase depend on how far along this line you come. So we're interested in, if we take a point along the central axis here, if we were to draw a line out to the actual function here, then this line here would be the magnitude, and this little angle in here in pink would be the phase. So we are interested in, how does this magnitude and phase vary with the frequency? So we'll go down onto the next slide and we'll look at the derivation of the magnitude and phase of a complex exponential. So we're saying that our function then can be look like a complex exponential that has a magnitude here, but of course the magnitude is dependent on the frequency, depends on how far along the frequency axis we go. So I'll just bring this back up here just so that you're sure of it. So what we're interested in is the length of this line dependent on the frequency. So we're over here this line would be heading up, say, this direction, and it would have a different length. We're over here, it would be coming up here. Again, it would be a different length. And we'd be interested in the angle as well, depending on that frequency. So let's work them out. We can say that in order to get those values, we're just going to use our Pythagoras theorem. So in order to get the length here, it's just a right angle triangle there. So it's just going to be that height squared. Well, that height squared is the real part squared plus the length there, which is the imaginary part squared. So the real part squared is just going to be the minus a upon omega squared plus a squared all squared. And the imaginary part is going to be minus I omega upon omega squared plus a squared all squared. And then we've got to take the square root of it. So let's go ahead and we'll go back down there and we'll do that just now. So it's going to be minus a upon omega squared plus a squared. And it's going to be all squared. So I wrote it out in full detail here, okay? So it's that times that plus that times that, which is a squared upon omega squared plus a squared all squared plus omega squared upon omega squared plus a squared all squared. So then we've got to take the square root of all of that. So we take the square root of that there. Then we can take the square root of the top line and the bottom line, and we get this here. Now, the interesting thing here, a useful thing to do, is we can write this in terms of powers. Okay, so rather than having the square root there, we could write that as omega squared plus a squared to the power of a half. And we could write the bottom line as omega squared plus a squared to the power of 1. So that's the same as omega squared plus a squared to the... Now, if it's a half and 1 and you're dividing, it's the same as subtracting the exponent. So it's a half minus 1, so it's to the power of minus a half. So that whole magnitude is going to be 1 upon omega squared plus a squared root. Okay, so we're saying then that this distance here is given by 1 upon omega squared plus a squared root. So if we can draw it out here, and that's the actual magnitude response. So each of these heights here represents this length from the 0 axis out to this function, this three-dimensional function here. And we get it by squaring the real part and squaring the imaginary part and then taking the square root. Now we'll look at the phase here as well. The phase here is given by inverse tan omega upon a. So the phase is this little angle here. Now you have to be careful here, because if we were to draw out the little phasor here, then we would have a real axis along here and our imaginary axis would be up here, and the 0 point, or the 0 degrees, is defined along this real axis. And whenever the exponential e to the I theta is equivalent to a negative or an anti-clockwise rotation. Okay, so it means that this little angle that we're interested in here, which is the phase angle, is going to be given by this length here divided by that length there. So it's going to be inverse tan y upon, so it's going to be the y upon x. So it's going to be inverse tan, well, this length here is the imaginary axis and this length here is the real axis. So it's inverse tan imaginary upon the real. So let's go ahead and we'll calculate that. So it's going to be inverse tan imaginary upon real. Well, the imaginary is minus omega upon omega squared plus a squared, and the real is minus a upon omega squared plus a squared. So these cancel out, and we're just left with the negatives cancel out, it'll be inverse tan omega upon a. So I've gone through that in quite a bit of detail, probably more detail than you would normally see, but I think it's quite worthwhile, because a lot of the time this kind of stuff is kind of brushed over, I think, whenever you're learning it. I'm not sure why they brush over it so quickly, but this is a good graphical representation of each of these components. So I hope that was of use to you, and I hope it was a decent video, and I'll get you in the next video. Goodbye.